All right, this is lesson 4.1 for our Pre-Calc 12 class. The new unit is called Polynomials. The lesson 1 is called A Problem That Speaks Volumes. So what we're going to learn about is what is that problem that speaks volumes and how it leads into polynomials, which will lead into a conversation of what is a polynomial function. And then we'll talk about a few words to describe polynomials. All right, so here's the problem. You have a box with some length L, which is equal to x. It's got a width, which is 2 less than x, and a height, a width is 1 less than x, and the height is 2 less than x. So what could x be in this context? We're not going to fully open this problem in this lesson, pun intended, but we are going to talk about the volume of this box. So the volume of a box is just length times width times height. If we know our length and width and height in terms of x, we can write it like this. The volume, or v of x, would be x times x minus 2 times x minus 1. And so this represents a polynomial equation. It's not in standard form, but it is a polynomial equation. And so let's talk about, there's many ways to represent this volume of the box. This is one of them. If we consider multiplying out that each of those polynomials into one big just string of x's being added or subtracted together, we do x times x minus 2, we get this guy, and then we FOIL these two polynomials and we multiply them, and we'll collect like terms, so we get the volume is x to the power of 3 minus 3x to the power of 2 plus 2x. Notice we have x cubed as our biggest exponent on x, which makes sense. The word cubed, we're talking about the volume of a cube. So when you see a polynomial like this, you can think of a cube. But let's talk about this equation right here a little bit more in depth. So if we graph this sucker, here's it graphed out as we originally had the equation. As we simplified it, it would be x to the power of 3 minus 3x squared plus 2x. Okay, as you can see, it is in fact the same graph. So we did algebra correctly. However, the question is, how does this relate to the volume of our cube? Well, let's look at this a little bit. We know that this thing crosses the x-axis 3 times at x equals 0, 1, and 2. The outputs are all 0. So that implies that when x equals 0, x equals 1, x equals 2, we're going to have a volume of 0 for our cube. A volume of 0. So that means we don't have any space inside the cube at all, right? So if we consider this x equals 0, that means, well, our length is 0. And if our length is 0, then we have 0 times something times something. Well, that equals 0. That makes sense. Our second 0 was when x equals 1. So basically when our width would be 0. So anything times 0 is still 0. And then if we consider when x was 2 was our last root, well, that makes the height 0, because anything times 0 times anything is also 0. So that kind of makes sense if we have those values of x. We don't really have a box anymore. We just have a flat surface of some kind, whether we diminish L, W, or H accordingly. And now if we have any value, really our box, for this context to make sense, we got to cut this graph down. So in light of those zeros, what is the smallest number that x actually could be? Well, x has to at least be greater than 0 for the length, but for the width, x has to be at least greater than 1, because you can't subtract 1 from a number smaller than 1 and still have some kind of measurement length. Doesn't make sense. But for the height, x has to be greater than 2 for this x minus 2 to make sense in terms of some kind of length. So we say x has to be greater than 2. This is the most restrictive piece of each of our x's. So if we look back at our graph, that means x has to be greater than 2. So any of these values for x would give us an actual volume of a box that's actually a box that actually makes sense. Okay, so there's lots of questions that I haven't answered yet that are going to remain unanswered for this lesson. For example, how can you get a negative volume like in this range or down here? And what about this range in here where we have a positive volume? How can that be? Well, we're not going to talk about that. I'm just going to leave that hanging there for you. So sorry for not giving you closure. However, we're going to unpack that polynomial in standard form a little bit more. So a polynomial function, if I were to explain it in the most complicated way possible, I would say it like this. A polynomial function is in the form f is some function of x such that a of n times x to the power of n plus a of n minus 1 to the power of x minus x to the power of n minus 1 plus and so on until my last term, just some constant number. So n is some whole number, as in like the first, the highest term, the second highest term, the third highest term, all the way down to the least term, or the initial term. X is the variable, so it'll just be x, or whatever independent variable we use. And we'll have a of n minus 1, a n minus 2, and so on, a1, a0, are all just some coefficient, some real number, whether it's a whole number or a fraction or whatever, some real number. Okay, so some examples here. We have examples and non-examples of polynomial functions. F of x is a polynomial function. We have x squared plus x, which would be to the power of 1, minus our a0 term, or our constant, minus 6. G of x is not a polynomial. That's a radical function. H of x is a linear function, and a linear function is an example of polynomials because it's in the form we have a coefficient times x to the power of 1 minus our constant. So this one is a polynomial. The next one is an exponential, not a polynomial. The base is 2 and the exponent is x. Polynomials have a base with an x, and the x has an exponent that is a number. But this is the opposite, so this doesn't work. Back at the top, this one equation is a polynomial. We have 4 terms. Each have a different power on the x. The next one is not a polynomial. It is x to the power of some real number, but our definition is that the exponents on those x's have to be whole numbers. Pi is not a whole number, it's a decimal. And then the next one doesn't work because of that I right there. I times x to the power of 2. I is not a real number, so we don't include that as not a valid coefficient. So for that reason, this is not a polynomial. If you get rid of the I and you just have y equals x squared, then it would be a polynomial, but it's not because of that I. Aye, capitan. All right, last one is y equals x to the power of 6. This is a polynomial. It is technically it's a monomial because it's only got one term, but it's in polynomial form, so we count that one. Okay, some words to describe polynomials. Degree. So here's our polynomial function for our box. The degree of a polynomial is the greatest exponent of y. So with our box example, the biggest exponent on any of these x's, the exponents are 3, 2, and the invisible 1. 3 is the biggest exponent, so our degree is 3. The leading term of the polynomial is the term with the greatest exponent of x. So where we found our degree will also tell us our leading term. So x to the power of 3 is our leading term. And the leading coefficient is the coefficient of that leading term. So because it's just a positive x, there's an invisible 1 out front. So 1 is the coefficient of our leading, or excuse me, 1 is our leading coefficient. And the constant term is whatever term has no x. So each of these terms have an x. So if you imagine there's a plus 0 attached, the constant would be 0. You could think of this as a term with an x to the power of 0, because x to the power of 0 would just be 1 anyways. That's another way people think about it sometimes. I'm probably not going to talk about it, but some people do. Okay, so some examples here. What are the degrees what are the leading terms, what are the leading coefficients and constant terms for each of these polynomials. So hopefully you can see some patterns here. If you want, you can even put your hand over the answers that we have filled in and see if you can work those out, see if they match up, or just see if they make sense to you. A couple of things to note. If we have a negative or a subtraction sign, we can call that as a negative in our leading term and our leading coefficient. Like minus x cubed, we have negative x cubed, we have negative 1. The terms without a constant, we just say the constant term is 0. Okay, so some takeaways. Hopefully we've got a little bit of exposure with polynomials. This is kind of our sticking our feet in the water. We'll go a lot more in depth on these in future lessons.